Alright everybody, how's it going? See some familiar faces again from last time. So Math Club is pretty happy to announce that we have our second grad student from Iowa State in a row. Last week we had O'Neill Kingston, and this week we have Adam Blumenthal. So Adam's going to give us a talk about some craft theory type stuff. It's called Independent Domination, Queens and Radio Towers. So, good job.
And thanks for the introduction, and thanks everyone for being here. I know that 2 weeks of Iowa State seminar might not be the most exciting, but I promise it will be different. And I hope to keep everyone involved. So, as a fair warning, I am going to ask questions. What's important to know about all of the questions that I ask is that this is a talk about my research, which means I hope you don't have all of the answers. If you do, then please talk to me. We have papers to write. Okay, but any guess, that's what I'm looking for. Just something. Cool? All right. So, we're going to talk about independent domination. And if you happened to read the abstract, the first question is Jaenish. In 1862, I can't pronounce anyone's name, so I'm just going to do my best. In 1862, we have a chessboard. We want to place queens on the chessboard so they don't attack each other and that they threaten every NP square. If you aren't a chess player, don't worry about those words. I'm about to tell you what they mean. Okay. So, how many queens can we place? What is the most or what is the least number of queens that we can place to satisfy these two conditions? Okay. So here's the first math lesson. We didn't take long. The first thing that you should always ask yourself when a mathematician asks you a question is this a trick question? Is there really a solution? Can I do this thing that they're asking me to do? Okay. And after you answer that question, you can move on to question number 2, which is what is the best way that I can do it? And Jaenish actually asked that on its own. What is the most or the least number of queens that could be placed? So, this is the math lesson of this talk. 2 questions. Can I do it? How do I do it best? So can I do it? Let's see if the technology favors me today. How about that? All right, it looks like we have technology. Sweet. All right, so I said I promised I'd tell you what a chessboard is. Here's a chessboard. It's an 8x8 grid. Okay. How does a queen move? Well, if I think, I can place a queen. These red squares are the squares that we say this queen could attack, because that's where the queen could move. So a queen can move any distance horizontally, vertically, or diagonally. All right, great. So the question was, how many of these queens can I place? Let's just place some. Does anyone have a favorite number between 1 and 8? 3. All right, 1, 2, 3. 1, 3, 5, 7, or 8? 7. Okay, great. So we can place another queen. There you go. And now it's going to get difficult to start guessing because, as you can see, we've threatened, well, that is, the queens could attack a lot of positions. So maybe I'll take the reins from here on. There's something I could place. Here's another one I could place. Here's one I could place. How about that? And here's another one I could place. So can I place queens that don't attack each other and threaten every other empty square? I guess so. It looks like I've done it with 7. So we've answered question number 1. Can I do this? Yeah, I guess so. And I can cheat now, and we can find out what the maximum and minimum number are. So do we want to cheat or do we want to take another try? Does someone want to give it a go?
Don't cheat.
Don't cheat. Does anyone want to give it a go? No winners or losers, right? You can do more or less or the same as me. No takers? All right, fine. I'll do it again. All right. I'll do it one more time. Okay, there you go. That's the spirit. You already know the answer to this? Are you going to do it correctly?
I know.
Okay, all right.
So 4 or less than 7?
Yeah.
I'm going to decide what that's going to be later.
Yeah, we'll figure out shortly whether or not it should be more or less. less than 7. All right, so that's right. So that's great. So we can get different numbers, so that's also good. Most and least are now a different thing. So now I will cheat because relatively shortly after I formally define all of these things, we're going to get a handout that includes the link to this website. And I'm going to give you free rein to stop paying attention to me because I have a new question for you. Okay? Once we know the maximum and minimum, here's the minimum. You can do it with 5 queens. Okay? Or the maximum, you can fit 8 queens. So the question that you can work on after I give you free rein to stop paying attention to me is how many different ways can you do this? And when I say different, I mean don't just turn the board 90 degrees. That's no fun. You've got to do something a little fundamentally different. So how many different ways? That's going to be the replacement question in lieu of the second half of this talk. Okay? So there we are. That's the talk. There's the 8-queen solution that I just showed you. And I'm a graph theorist, which means that I solve problems by making graphs. And whenever anyone asks me, what do? I study dots and lines, and then they look at me and they say, that was very condescending. You can explain it to me in more detail than that. And I say, no, really, I study dots and lines. I model problems as vertices, or dots, and some relationships between them. And those are lines, or edges. Okay, so that's really what I do. I model problems with dots and lines, or vertices and edges. So I guess that's what I'm going to do here. All right, so the first thing I'll do, replace each square with a dot. Fair enough. And what's the relationship that I'm interested in for these squares? What can a queen do? A queen can move, right? So what do I want to do? The relationship is, can a queen move from one square to the other? That's how I'll add my edges. Can a queen move from one square to another? So, for example, the bottom left square, let's add all of the edges that should be present. Well, so they can move in any direction as far as they want. They can move up and down as far as they want. So there's a bunch of edges. They can move horizontally as much as they want. There's a bunch of edges. And they can move diagonally as much as they want. There's a bunch more edges. And that's just all of the edges incident to this one vertex. So we have to do that again for every single vertex if we want to model this as a graph. Which suddenly becomes completely unrealistic to look at. And we might need a computer to help us. Because this is going to be a big line blob. So we're going to not do that. Let's instead talk about why do I care about graph theory? What questions are graphs good at answering? So I have a few of my personal favorites written here. One of them, I would be remiss not to mention, okay? This is, if I have a map of, I don't know, countries, states, whatever you like, how many colors do I need to make sure that no neighboring states or countries have the same color? I want to color every state. Okay, that's one question I could ask that is very famous in graph theory. Another question that I could ask. All right, this one is maybe a more practical problem. This is, I have a gas company, an electric company, and a water company. I also have 3 houses. Can I add pipes between each of these companies to get gas, electricity, and water to every house so that they don't cross? Because the water crossing the electricity seems like a bad plan. So can I do this? Can I make sure that none of these cross? Right? So this one is important. Will I ever be happily married? And I hope so. I am happily engaged currently, so hopefully that progresses forward. But graph theory is going to answer this question for me. Okay? So let's go back through the problems. What might I use for vertices in the map problem? The countries, right? I want to color each country a different thing, so probably model the countries as vertices. And the relationship, I guess, would be, well, I care about their neighboring countries. So that's the relationship I care about. And it turns out that this is the most famous theorem in graph theory, at least according to me. And it's the four-color theorem. You can do this no matter what map you draw, whatever fantasy land you have. You can do it with 4 colors. Okay? How about this practical problem with utilities? I guess the factories might be vertices and the houses might be vertices. And the pipes make pretty natural edges. You actually would have to cross at least once. And this is Kuratowski's theorem. And will I ever be happily married? If mathematicians controlled the world, then yes. This is the stable marriage theorem. So these are all theorems using graph theoretical techniques or just straight up graph theory. So this is why we care about graph theory and why we hope that maybe we can solve this question about queens with graph theory. Okay, so let's go back to our problem. There were 2 conditions that we had. The queens needed to not be able to attack each other, and they needed to attack every other square. So what does it mean to be non-attacking on a graph? Here's a much simpler graph, much better than the queen's graph that we had drawn before. And there were 2 questions that I said at the very beginning of the talk. Does anyone remember what the first question was? Can it be done? Can I place non-attacking queens? Sure. Here's a really lame way to do it. Just place 1. It certainly isn't being attacked by any other queen. That's an easy solution. So I guess question 2 is, what's the most or least? What's the best I can do? Well, that would be, this is the easy one. I guess the hard one is, what's the most I can do? So can I do more here? Well, what does it mean to be attacking? Well, there's an edge between the 2 vertices. So are there any vertices here that I could choose that don't have an edge to the vertex I've already chosen? I see some nods. Yeah, there are. Anything on the right-hand side over there is good. So maybe I'll take the top right. And now I can't place any. Okay, so on this graph, maybe 2 is the best I can do. And it does exist, so that's good. We're going to call these an independent set from now on. If I say non-attacking, someone wave their hands at me. Okay, we're formalizing now. This is real graph theory, right? Okay, so this is an independent set, and an independent set just means there are no edges between the vertices you've chosen. No edges. Independent set. Okay. So we have another condition. That's threatening every square. Does everyone have an idea for a really lame way to make sure that I threaten every square that isn't chosen? Taking 1 probably isn't going to work. What's the opposite of that? Yeah, take all but 1 of them, right? That's definitely going to threaten all of the squares that I didn't take. There you go. I can take them. So there's the easy solution. So the hard version of this problem is take the least number that you can. And certainly I could do better than these 5. Here's one way. Just those bottom 2. So if the pointer works, let's see. Ah, yeah, okay, great. So here, this is called a dominating set. That is the property that you have an edge to everything not in your set. Let's check and make sure that that's true of these 2. This isn't in the set, this wasn't chosen. So yeah, there's an edge to it. Here, actually there are 2 edges to that middle one, and then the top one, there's an edge. Okay, good. So this is what we're going to call a dominating set. So So we've got independent sets, no edges, and dominating sets, edges to everything else. Okay. But question 2 was, what's the best I can do? Is this the smallest dominating set that I could choose? Can anyone see a smaller one? Yeah. Yeah, the middle is adjacent or has edges to every other vertex. So there you go, 1. That's the best that I could possibly hope for. I'm going to have to take something. So here, 1 is the size of the smallest dominant. Okay. But we needed both of these conditions. Non-attacking and threat in every empty square. So not to belabor the point too much, here's one of them. But again, we should be asking ourselves, what's the best I could do? Am I looking for large sets like this, or small sets like this? And I think that this time it's less clear. Here's a smaller one. Okay, great. We're going to call these independent dominating because we aren't very creative, because it has the independent property and the dominating property. There are no edges between the vertices I've chosen in either of these pictures, and they have an edge to everything else. So, independent sets, we want large ones. Dominating sets, we want small ones. Independent dominating sets. Half of it is hard to make large, and half of it is hard to make small. So it's not clear to me what's the best choice. What's the difficult one? Maybe they're both difficult. Maybe neither of them are difficult. If neither of them are difficult, then we'll probably leave soon. So maybe fingers crossed. Okay. And importantly, whenever we're thinking about math, we should think about how it's related to other things. So how are all of these things related? Independent sets, dominating sets, and independent dominating sets. And now it's audience participation time. So I have a bunch of handouts for you guys to give this a shot. We have 3 graphs. I guess I'm going to do my best. As I have. Yes. So feel free to yell at me when it doesn't make any sense.
Does anybody not have one?
I gave all mine away. Yeah. Also, please, this is not an individual exam. Talk to your neighbor.
Was there any kind of difference? The second one. Wait. You don't have to cover every edge. It's just.
That's a good question. Actually, the same thing. I think I agree with that. Sometimes there is sense. Sometimes.
Although for this one, those aren't independent. The way bottom right. Just need a tricky one.
Good.
Good.
Yeah.
Getting there.
Tricky one.
All right.
I think.
I think so. These look good.
So for this one, would this be kind of the same here? Because I feel like for this one, the limiting factor is like I can't touch other stuff like this,
Yep.
like whatever. So
Yep.
this just be this.
Mhm.
Okay.
You're catching on to my devious tricks already. All right. So it looks like most people have done at least a couple of these. So let's come together. I have solutions. So that's good. You can check and compare. So we'll go through in order. First, smallest dominating set. So we can check and see how we did. Okay, so that top left graph, which I'll call a cycle from now on, it looks sort of like a circle, but with vertices on it. Okay, we make a regular end gone. Okay, there are two. That's the best that I can do. Over on the top right, we have one, because that vertex touches every other vertex. That's awesome. That's the best we can possibly do. And then here, we've got these two special vertices in the middle, which touch all of those sort of vaguely bits out towards the end. So 2, 1, and 2 for smallest dominating set. And here we are for independent sets. 2, this one changed. Okay, I can make a larger independent set than I can make a dominating set. Okay. And then this one also changed a lot. So instead of taking those two middle ones that were sort of efficiently covering everything or dominated everything, we now take those leaves because they don't touch very much. So this is sort of the opposite of what we wanted with domination. It is what we want with independence. And now we're going to go to the largest independent dominating set. And I want everyone to make sure that they don't blink, so everyone eyes glued. Okay, hold on. Let's do it again. There's a dependent. There's a dependent dominating largest. What happened? They're the same. They're the same. Sweet. So maybe that's a hard question, but it's a question that we've already asked. Largest independent dominating sets are the same as largest independent sets. That's cool. So there is some relationship between them. So hopefully the hard question about independent dominating is what's the smallest one. And here I get 2, 1, 3. 3 is a new number. I haven't ever seen that before. So somehow they can all be different. So as a mathematician, I have to ask myself, can I order them nicely? Can I order them nicely? Well, okay. So here's a nice property. We notice that largest independent dominating sets are the same as largest independent sets. That's true in general. There's a one-sentence proof of it. But I'd rather draw a picture instead of the proof. Here are all of my independent sets. And over here, independent dominating is independent and requires an additional property, dominating. So here are my independent dominating sets. Here's the proof. The largest independent set is definitely larger than the smallest thing in here, because this is also an independent set. Ta-da, we've done a proof. We're all now officially full-fledged mathematicians. Okay, cool. Here's another one that's the exact same proof, just words interchanged a little bit. The smallest dominating set is always smaller than the smallest independent dominating set. Because again, we're just requiring an additional constraint. Take a dominating set, ask if it's independent. If it is, it still counts. If not, throw it out. All right. So here we are. Smallest dominating set, size 2. Smallest independent dominating set, size 3. Largest independent set, size 4. So these are all different parameters. We haven't wasted all of our time. So this is the point where I want to stop and say, on the handout, there's a link to the website. If you just want to place queens for the rest of the talk, feel free. You've gotten through the definitions, you've made it. Okay? So place queens, and the question was, what's the most different number of ways that you can place 8 queens? That's where I'm interested in. So if you want to fiddle on your phone or on your computer to try and solve that, go for it. The rest of us will continue on. Okay. There it is. The question that we started with of Jaenish. But I am a mathematician, which means I like to generalize. So instead of just an 8x8 chessboard, why don't we talk about larger chessboards? 10 by 10, 20 by 20, 100 by 100, 376 by 376, whatever your favorite number is. N by N chessboards. How many queens can we place? It turns out that this is still open, despite basically having been asked 200 years ago. Which is pretty cool, I think. More or less, we know that it's between half of the length of your board and a little more than half of the length of your board. Okay. I wrote kind of here because if you ever get involved in extremal graph theory, there's a little O of one term here, so it's off a little, but only a little bit. For large N, this is true, basically. Okay, and I want to say, the problem is really old, 1862. This upper bound is from 2007. It's been a long time. A lot of people have worked on it, so if you can improve that, then maybe you're famous all of a sudden. So that's cool. But that's hard. So let's go to a different context. Directed graphs, which is maybe exactly what you think it is when I say directed graphs. It's a graph that's directed. A graph that's directed. I put arrows on all of the edges. Congratulations, you know what a directed graph is. Okay. It's a graph where all of the edges have a direction. A vertex points to another vertex. Okay? And you say to me, Adam, I know you warned me that you're a mathematician, so you like to generalize things, and maybe that's all you're doing here. But why do I care about a directed graph? I got 3 reasons for you. Some relationships aren't two-way, and that's true both in a social standpoint, but also in a mathematical one, right? think about seeing over a hill, right? If I want to say the edges are everywhere that I can see, if I'm on top of a hill, I can see in every direction. If I'm on one side of the hill, I can't see through the hill. So it really is a one-sided relationship to see over, around, or through a hill. Another thing that's sort of a more classical example, one-way roads. Sure, this is almost always how they're introduced first, which means it's not very interesting. Next one, communication networks. This is the one that is particularly interesting to me. So domination and independent domination are very valuable in communication networks because they tell us efficient ways to place radio towers or phone towers, right? You want to make sure everyone has service. What does that sound like? Make sure everyone is touched by something. Domination. So there you go. All of a sudden, these directed graphs give us access to real-world problems that we're solving. All right. Here's a full-fledged proof, because I've been told by my advisors and many others that there is no math talk is complete without a proof and a joke, and hopefully they are not the same thing. So here's our proof, and you can decide whether or not it's also the joke. All right. So, oh, sorry, I lied. There's the joke. Ha-ha! We have to define things first. What's an independent set? It's the same as before. There are no edges. Doesn't depend on direction at all. Does it exist? Yes. It existed before. There's one. Ta-da! And they will always exist. So that's nice. How about this one? Directed domination. This one depends on direction, because domination is going to count only forward. If I point forward, I will dominate that vertex. If I see that vertex, I will dominate. Okay. Do these always exist? Well, let's try the undirected version. It worked for independent. There it is. Great. Now I direct the edges again. And so this formerly dominating set, oh no. Formerly dominating set dominates forward to this vertex. That's good. Dominates forward to this vertex. That's good. Dominates forward to this vertex. But there's one more vertex that points to it. So it's not a dominating set in the directed sense. There's the problem. Can I fix it? Yeah, okay. Someone nodded once I nodded. I can fix it. Let's just add another vertex. There it is. Now it's dominating because that vertex points to this. So we're in good shape. So here it is. Independent dominating sets. In directed graphs, it's independent is directed dominating. Exactly what you'd expect it to be. And I've been training you guys to ask one question first always. What's that question? Can it be done? Yeah. Is it possible? Does this make sense? Here's a graph. Yes, it can be done on this graph. Good. So surely it will always work. Or perhaps I've been asking this question the whole time because it's surprising that sometimes it doesn't. Also, this is good work. 2019. Cool. All right. Anyway, sometimes it doesn't. All right. So let's go through this together. Place a vertex. Good. Great. Cool. There's the first one that I've chosen. You might be able to convince yourself that it didn't matter which one I picked because they all look the same. Great. Place another vertex. Over on the right, I'm sort of forced. If I want it to be independent, there's only one choice. Over on the left, there are kind of two choices, but really I think they're the same if you rotate your head far enough. But it might be difficult. So there we go. All right. So the right-hand one is good. I have this vertex is dominated here. This vertex is dominated by the one on the right here. This one dominated here. Dominated here. Uh-oh. So I would need to add another vertex to dominate that. But I can't, because it wouldn't be independent anymore if I pick either that vertex or the one below it, because I've already chosen this vertex, I've already chosen this vertex, uh-oh. So there's really a problem. These don't always exist, which is horrifying, because if I want like radio towers to be placed, I want there to be a good way to place them. And here we go, there's not always. Okay. Here's the proof. And since we've already gone through the joke where I told you that there was going to be a proof and then there wasn't, surely this is good. So what are we going to do? I was scared of this sort of structure. A cycle, an odd cycle was scary. So remove all of them. There are no more cycles. That means I can never get back to myself. No path will ever follow back to itself. Turns out, if I guarantee that, I always get an independent dominant set. Here's the proof. I found a special vertex. Here it is. There's something very special about the edges from this vertex. What's special about the edges from this vertex? I heard a mumble. No takers?
They're all leaving.
They're all leaving. Yeah. So, how about I'm going to pull this out. There it is. Okay. Let's look at what's left over. Can I find a similarly special vertex? One where everything is leaving. I see a nod. So over here on the right, well, surely this is going to point to it. Oh well. Ignore this guy. What's left? It's just point out, point out, point out. All right, pull that guy out. We're going to make an ordering. That's what's happening. Make an ordering of our vertices. All right, look again. Can I do it? Can I find another one that points out to everything that's left? Sure. The top points out to everything that's left. Take it out. There at the bottom, these last two here, this points out to everything that's left. Fantastic. And then I guess the last one I'll just bring up. So what I've done is created what's called a topological ordering, which can always be done for directed acyclic graphs. And why is this nice? If I want to dominate this leftmost vertex, how am I going to have to do it? Well, I can't take anything that points to it, can I? So I guess it's going to have to be in my independent dominating set. So put it in. There it is. Oh, but now I can't pick a bunch of things because they wouldn't be independent. So I'll mark those out. Those are bad. I can't choose those. And now what's left is the rest of the ordering. I know that if I pick the leftmost thing, it's not going to be pointed to by anything previously chosen, or else I would have marked it out already. Ta-da! I can pick this, and I can keep going if I had to. There's an independent dominating set. And if you don't believe me that it exists in the original graph, here it is. There's the independent dominating set. Points out to this guy, points out to this guy, points out to this guy. Great. And then this one was left over. So I had to take it. And it was independent, so I'm in good shape. Okay. Great. So the proof is keep taking a source vertex, that is one that only points out, until you can't take it. That's the whole proof. Ta-da, you did it. You found an independent dominating set. Not so bad. So, where do I go from here? We'll go to something that is related to those cycles. It was getting back to yourself that was scary. So let's go to a graph where no matter which vertex you pick, you can get to any other vertex, and you can get back to yourself, which sounds like the worst thing that I could possibly pick to do, right? Because everything can get back to itself. We'll call that a strongly connected graph. And a strongly connected component is a little piece of that graph where this is true. So for example here, if I wanted to get from the bottom left vertex to the top left vertex, I could follow an edge forward, follow an edge forward, follow an edge forward, 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 forward. Oh, I could get there, but I had to get back. So follow forward, I can't jump to this other circle. So I guess follow forward again. I still can't jump to the other circle. So this graph, the big graph, is not strongly connected. But these little circles are. No matter which vertex I pick in here, I can get between them. That's a cycle. I'm gonna cycle down here, cycle this way. Cool. So I can take these strongly connected components, push them all together, mush them together, so they look like one big vertex. So there they are. And now we can look at what does the big graph look like. I've got my new vertices, my edges, I'll draw according to if I could get from one component to the next. So if I can get from this circle, if I can get from this circle to this circle, I'll draw an edge there, and I'll put it in the direction of all of the edges. Turns out they're all going to be the same. There you go. So we add all of these edges. This one can get forward to here, and this bottom right goes forward to the top. So I've got a smaller graph that is acyclic. And we just said that acyclic graphs are easy to deal with. That was the last slide. That was the proof we did. Acyclic graphs are nice. So can we take advantage of it? Okay, I have to bore you with yet another definition, and this one is particularly odd. Even graph theorists probably don't know this one off the top of their head. It's the period of a directed graph. Actually, if you took college algebra recently, you're more prepared for this definition than I am. So it's the greatest common divisor of the lengths of the cycles. So, for example, here's a cycle. It's got length 3. Here's another cycle. It's got length 4. And I need to figure out what in the world the greatest common divisor of those two things are. That's the largest number that divides both. So 3 doesn't divide 3 and 4. 2 doesn't divide 3 and 4. 1 does. So this has period 1. The fish has period 1. Okay? Here's a little more complicated graph. I see I have a 3 cycle here, a 3 cycle here, and a 6 cycle. So what divides 3, 3, and 6? 3. So this has period 3. Okay. So here's a graph, let's solve it. No big deal. Turns out that if you have an even period, this problem is easy. You can always find an independent dominating set. And since you've all had about 5 seconds to look at this graph, I'm sure that you've determined this is indeed a graph with even period. It has period 4. But you don't need me to tell you that. I'm sure you can tell. So this has period 4. And one of the cool things about this research is that it uses techniques from multiple fields. So through the magic of linear algebra, I'm going to redraw this graph. Kind of. Okay, I've redrawn the graph kind of. What's going on here? Notice 4 was a special number, it had period 4. There are 4 blobs. Inside each blob, there are no edges. Edges only appear according to these gray edges that I've drawn. So they sort of only point forward. It looks like a problem we've already solved, which is nice. Even cycles were easy. We just take a vertex, and then the next one that we can take, and then the next one that we can take, and eventually we stop and everything is fine. Okay. So there's the theorem, if I can move forward. Ooh, those sets are independent. Nice. And they point forward to everything in the next block. Thanks, Frobenius. You're the man. And there's an independent dominating set. We found it. So it turns out the question is not that hard when you have the right question that you've asked. But in general, it's still super hard, so please, if you know how to find these things, let me know. And I think that's all I've got. But before the end, Did anyone come up with lots of ways to place 8 queens? Anyone come up with any other ways? Does everyone want to take a stab at how many ways there are to do it that are actually different? Yeah. One. It's more than one. More than one. It's 12. There are 12 different ways to place 8 queens, which sounds like a lot, but really it's not very many with how many different ways you can place queens. So it's very uncommon, yeah.
Does that include rotating?
That's without rotation. Yeah. 12 without rotation. Or reflections.
So if you rotate this 90,
That doesn't count. That's not a new one, that's the same one. It's not fair, you just walked around the board. Okay, you've got to do something more interesting than that. But yeah, so there are 12. Alright? And I think that's actually all I've got.
Anyone have any questions for Adam?
Okay. So you mentioned linear algebra, but then what's the linear algebra? Can you just briefly tell me about the linear algebra that happens?
Yeah, so I avoided it because it's mildly technical. So it's a consequence of Perron Tremedius, which says something about eigenvalues for some matrix. If you take in linear algebra, that's great. And it gives us a way to partition the graph so that we have those nice big empty blobs. That's what it means.
Those empty blobs were related to eigenvalues?
Yeah. Yeah, wild, right? Empty blobs are related to eigenvalues. Independent sets and linear algebra are all the same thing. They're just different names. Crazy. Math is really interconnected sometimes. All of the times.
All right, let's give Adam another round of applause. Everybody want to come down for another picture like we did last time?
Okay. It's fine. We're in now. It's fine. You can take another little piece of my soul. You've got tall people. That's right, we'll count the heads. All right.
Everyone ready? You say everybody? Are we ready? All right, 3, 2, 1.
Thanks everyone for coming.
I messed up the good.
Yes, is there some like the